take a look at a demo. Okay, so I've come up with I wrote like a little program that sort of illustrates proof of work and how it's used in mining. And okay, we'll go ahead and launch this. And this is an important demonstration because I think it shows the concept of difficulty and what actually happens during proof of work. So talking about difficulty, like let's look at let's run a hashing function, SHA-256, and let's give it an input of hello underscore, let's just give it an input of hello. Okay. If we run this through SHA-256, we get a 256-bit output, 64-character hexadecimal number. And this is unique to the string hello. Now, if we look at the very beginning of this, there's no 0 in the beginning. And when in the context of a Bitcoin discussion, when somebody says difficulty target, they're referring to the number of zeros that appear in the beginning of this 256-bit output. So in this case, there are no zeros. But if we were to guess again, and so let's just say hello 1, again, there's no zeros. And then if we guess again, hello 2, still no zeros, right? But if you notice, all of these are very different. They're completely different. Like these two happen to start with a 7, but that's just by luck. There's just no pattern to this, right, that we can decipher. Now, if we keep on guessing, eventually we'll get to an output. If we keep incrementing this up, we'll eventually get to an output of 0 an output that has a 0 in the front. And so what I did was I wrote a little function that says do work that'll keep guessing until we get to one that has a 0 in the front. So if we run this do work function, boom, in the blink of an eye, we've now guessed 14 times. It's actually 15 because this is 0 indexed. So we just add 1 to this. So we've guessed 15 times, and we've got an output that starts with 0. And it took us 15 guesses. Not hard at all, right? That can be done very, very quickly. But if we change this code to look for 2 zeros in the front, and I'm just going to reload this. Okay, so we reload it, and then we run again. Boom, still a blink of an eye, but notice how we've had to do 73 guesses, actually 74, before we got to an output that is 2 zeros. So, that's a difference of 15 to 74. That's exponential, right? Like that's a lot harder just by adding 1 0. Let's go ahead and add another 0. So now our difficulty target is 3 zeros. Reload the file, run it again, and boom, still quick, in less than a second, but we've guessed almost 7,000 times before we got an output that has 3 zeros in the front. Right? And this number, which is just 1 less than this one, this number is just 1 less. Look, completely different output. But anyway, the point is we got an output starting with 3 zeros. It took us about 7,000 guesses. Again, exponential. We went from 15 to 74 to now almost 7,000. Let's try it again. Let's do 4 zeros as the new difficulty target. Now, load that. Let's see how long this takes approximately. Do work. Okay, now we took us 33,000 guesses. So we went from 7,000 to 33,000 guesses. And now we have 4 zeros. And again, the only thing we're changing is the number. We're incrementing by 1 every time. Completely different output. Interesting, this has 2 zeros for that one number. But again, this is not relevant. We were looking for 4, so it doesn't matter what that one had. So what matters is that it was a lot more work every time we add a 0. And let's just do one more here, because this one really is like kind of really hammers the point home. So now we're looking for 5 zeros. Look at this. It's taking many seconds now. Still going. Now we're probably at 10, 15 seconds. Okay, boom. So it took us like, at least 15, 20 seconds to do this by just requiring one more zero, and it was almost a million guesses. It went from 33,000 to a million guesses. So as you can see, it's exponential. As you add every zero, it becomes exponentially more difficult to solve this, to guess, hello plus any number, any random number here that we just add to it to get that. Now, if you want to know where we're at today when it comes to like the real Bitcoin blockchain, we can look at a block here on just any blockchain explorer you want, and look at the block hash. Look how many zeros it has in the front. So that's a massive, massive amount of guessing that had to be done. And if we think about this hello, that hello can be considered the block. And we'll get into what a block is in just a moment. But this number that we've incremented up by 1 every time we've guessed is actually, the only purpose it serves is just another number, another random number that we add to the useful block, the useful payload, I guess you can say, plus a random number run through SHA-256 to give us an output. So this random number, again, it's not random because we're incrementing by 1, but it might as well be random. It doesn't matter that we're incrementing by 1 every time. We're just trying different numbers and seeing until we get what we want. So we'll call it a random number, is actually known as the nonce, and that's what's listed here. And so what's really happening with mining is that we're taking, this is an example of a block. We're taking a block, throwing a bunch of transactions into it, like when people are paying each other, that data into the block. We're adding, timestamp, some other metadata. The Merkle root represents the transactions. And then the previous block's header hash, right? So we have to reference what was there before, because remember, if anything changes, even just one character, the output is completely different. So if we reference something that was already on the blockchain, then that means that if something prior to this, a long time ago in history, changes, it changes the whole course of the blockchain going forward. That's not really part of this discussion, so I'm gonna backtrack here. So basically, what a block is, the block contains transactions and some other metadata, and then it runs it through SHA-256, and it gets an output, right? Here's a bunch of zeros. This is the header, this is the hash output. So if that output doesn't start with a bunch of zeros, then we need to change this random number, which is the nonce. Let's bump it up by 1, run it through SHA-256 again, and see what the output is. Oh, nope, that doesn't have enough zeros. Okay, let's run it again, see what the output is with the different nonce. Nope, doesn't have any zeros. Okay, let's run it again. And that constant process of guessing, right, which is really just brute forcing, is what proof of work is. And so basically, if you guess enough, eventually, and you keep trying different random numbers in the nonce, then eventually you will find, you'll get an output that satisfies the difficulty target. And that's how a block is actually created. So as you can see, this process of guessing is what proof of work is, but the process of grabbing a block with specific data and then a block that references the previous block's header hash, and then running that through SHA-256, that process is what mining actually is. Now, I would go further, a little further. I mean, you could probably stop there and say, okay, that's the concept of mining in a nutshell. But an important addition to that is the concept of propagation. So basically, I'll try and cover this as quickly as I can, not relevant to this discussion. But so let's say that these are 4 different blockchains, right? These are 4 different miners. Each column, like miner 1, miner 2, miner 3, miner 4. And each of these blocks represents the blockchain as it currently stands. Now all 4 miners, this is the tip of the blockchain, like the most recent block. Now all 4 of these miners are mining, they're guessing, they're taking the block, stuffing transactions into it, stuffing the previous block's header hash into it, and then adding a nonce, taking that data and running it through SHA-256 and looking at the output and seeing if it satisfies the difficulty target. So that's happening for all 4 of them. They're all guessing as quickly as they can. This block, this miner, gets a solution. And so what does this miner do? It starts propagating to the rest of the network. So saying, hey, I got the block. This miner receives it. The first thing they do is they validate it according to the Bitcoin consensus rules. And they say, okay, are the transactions correct? Are, just whatever consensus rules that, the Bitcoin protocol contains. It takes that, importantly, it takes the hash with a bunch of zeros this miner solved that block. It takes that hash and then verifies it. So it runs it through SHA-256, gets the same, so basically it takes this block, runs it through SHA-256 and is able to quickly verify that the output is what this miner got. And again, because with hashing functions, you cannot guess the input, right? By looking at the output. But if you're given the input and you're given the output and told to validate it, that can be done very easily. So that's what this miner does. Quickly comes to the conclusion that, yep, he's right. And then passes that on to the next one. And so before you know it, all of these miners now have this version of the blockchain, because this one was the longest, which then propagated to all the rest of them. All the miners independently verified that the block was correct. And as soon as they verified it, they're immediately starting to work on the following block. And they're doing all these guesses, and they're hashing, and the whole process begins again. It's a race. And so that's the essence of propagation. But that's, kind of like the perfect scenario. But in reality, that doesn't kind of address, the consensus the novelty of the consensus algorithm, in the sense that what if you have a miner in the southern hemisphere in Australia, and you have another one in New York, right? So let's say that because it's completely random, let's say that they both are able to solve the block at the exact same time, or within milliseconds of each other, and they start the process of propagation to the network, and they do it in such close proximity that basically half the world. I'm going to actually change color. I'll call this red. I'll call this blue. Okay. So they both solve a block, and at almost the same time they start propagating to the network, and half the world has red, half the world is blue. Because remember, this is possible because if both of them legitimately solve the block, then you have 2 versions of the blockchain that satisfy the consensus rules, and therefore half the network has red, half the network has blue. But remember, mining for the following block happens as soon as you validated the current block. So they all start mining for the next one. And now let's say the next one, this miner solves the block, and this miner starts propagating. They validate it's true, and then this miner tells this miner, and it spreads across the network in its entirety. Well, what happens in this case? What happens is, remember, each block is referential to the previous block, right? Like this block contains the transactions, the nonce, plus the header hash of the previous block. And this one contains the hash of the previous block, going all the way back to the very beginning, the Genesis block. So that's part of how these blocks are validated. So when this one when this miner attempts to validate this block, they quickly realize that the previous block's header hash does not match what's in here. And so what they say is, okay, something's wrong. And they say, does anybody else, they start reaching out for the previous block. This is not exactly what happens, but this is an easy way to kind of explain it. They'll start reaching out to other blocks and say, hey, I'm looking for block with this header hash. Oh, here's one. And then they'll kind of pull that in. And then if there's another one, if this scenario happened where it was too deep, it would just happen again. And so basically, before you know it, the block converges onto one source of truth eventually, right? So even if there's a tie, even if there's two ties in a row, what eventually happens is they'll converge on one source of truth as soon as one version of the blockchain pulls ahead of the other, and that's what's referred to as the longest chain. And when I said this wasn't accurate, that's only because, like, instead of necessarily reaching out, they probably already have, I think they already have candidate blocks. Like in a situation where there's a tie, they would also kind of hold onto the candidate block until they converge or something like that. I don't remember the exact technicalities of it, but that's how propagation works. So yeah, I think I'm gonna stop it at that. Stop right there, because yeah, we're already about 30 minutes, but helpful to people, because really, Bitcoin is both simple and really complex at the same time, and trying to explain this is extremely difficult, and I wanted to have some sort of reference that I could point people to instead of having to explain this every single time, especially something with visuals. So hope you enjoyed it, and if you have any questions, please leave a comment and I'll do my best to answer them. Thank you.